Hello everyone, our topic is named semantic segmentation for pedestrian detection from motion in temporal domain. In real-time autonomous driving, the semantic segmentation is one of the well-known vision tasks. The traditional methods for pedestrian detection in the driving video is that they directly deal in the spatial space, which is time-consuming. In our work, we apply a thorough pedestrian motion segmentation and detection in a temporal spatial approach, which is very fast with minimal latency in driving. Then we can perform sequential semantic segmentation for the reduced data in a 2D temporal layout. Here is an example for the overview of our method on this reduced data view. The video for autonomous vehicle embedded hardware had limited capacity of computation and memory, so we proposed this method to reduce the 3D video into a 2D image layout. First, we sample in each frame at a belt predefined below the horizon. Then we condense each belt into 1D array by averaging pixels vertically. Third, these 1D arrays from consecutive frames are copied into a spatial temporal image named motion profile. The motion profile will have the same width of the frame image, and the height of the MP is the total number of frames in the video. Though only 1D data are sampled from each frame, their temporal concatenation shows motion characters. The pedestrian motion in MP will form a very unique physical shape as one crossing chain in the motion profile. So we can apply this unique physical shape in deep learning based method for semantic segmentation. For the sake of detecting pedestrians at multiple distance from the camera view, we extract 3 MPs at near, middle, far, which are useful for path planning. Here are the example of the MPs at 3 different distances. Besides, we can also track the MPs from different sensors, including camera and LiDAR. The pedestrian motion will form multiple patterns in MP, including the skewed legs when the vehicle is driving fast and making turning. We predefined 3 semantic classes, including the pedestrian in motion, human standing still, and the background. Then we perform the sequential segmentation along the time axis in the motion profile by cutting off a small patch size of the 32 frames along time axis. Then we horizontally resize this small patch into 256 in the width. Here example of the sequential patch size along the time axis in motion profile. To make our model depth invariant, we horizontally divide the far, mid, and the near motion profile into 3 columns respectively, and then resize them horizontally into the same width, so that our training model can be depth invariant. Then we apply one encoder-decoder module with skip connections or the architecture of deep neural networks to perform sequential segmentation. It has 5 encoding layers and 5 decoding layers. To phase out the redundant information in the overlap data between 2 consecutive patch sites when we are scanning the motion profile on the time axis, we perform one novel method named temporal shift memory. it is a reference model which is only applied in the testing phase, and it also accuracy lossless. The TSM avoids repeated computation by storing previous computed nodes hierarchically. At each layer, only the latest nodes are updated through the filtering and maximum pooling. Here example of the TSM we illustrate for 3 layers. Then we perform the experiment on multiple benchmarks. Here are the example of the quantitative results we achieved from our method. Then we evaluate the method by calculating the pixel-wide accuracy and the frame-wide detection rate. These are the results of our detection rate. Then we compare our method with other state-of-art, including motion filter and the YOLO 3. Compared to YOLO 3, we have we use the less state of computation and achieve the fast computed time and praise a better motion continuities. Therefore, our method with the minimum data size and low variation of motion patterns to perform the sequential segmentation in 2D image layout, the algorithm complexity is very small and the detection speed is drastically faster than all the other state-of-the-art methods so far. Thank you.